Hi, I'm going to tell you about long-term ear-EEG, why it is cool and what it takes to study the brain activity in daily life. So we are all here because we are interested in how the brain works. We study brains to learn something about ourselves. And unlike introspection or observation of behavior, we can use EEG to examine the workings of the brain that are otherwise hidden from view. Moreover, unlike invasive methods or lesion studies, we can use them to observe what the healthy brain does. We have come a long way from the first recordings of Hans Berger, and today EEG is widely used for scientific, diagnostic, and therapeutic purposes. Yet, most of what we have learned about the brain using EEG, as we have heard, we have learned in the lab. We have learned it from weird subjects in basic experiments. So weird subjects is a term coined in a paper by Heinrich et al., the weirdest people in the world. In this paper, they point out that most studies conducted in psychology is conducted in participants that are undergrad psychology students, Western students, highly educated, that live in rich and democratic societies. And relative to the global population, this is just a minority. So our results may be highly skewed and generalize poorly to the population as a whole. Moreover, in any imaging study, including EEG, we skew the data in another way, as we already have heard. And the imaging studies we conduct are very brief, rarely exceed 2 hours. We conduct the studies in artificial environments while the participant is stationary, isolated without any social interaction, as we have also just heard, and highly controlled in what she sees or hears or is allowed to do. So both regarding the diversity of people and the diversity of situations, we have just sampled from a fraction of human experience. With mobile EEG now, we have a wider perspective. In recent years, we have seen a great shift in neuroscience. We have overcome many of the constraints I just mentioned. Now we study freely moving people in complex virtual environments during social interactions, and even during outdoor experiments. In Oldenburg, we have contributed to this development by working on making mobile EEG transparent. The idea behind transparency is that both the wearer and other people can forget about the hardware. So we started with hiding electrodes in a baseball cap and in and around the ears, and later developed the secret, an electrode array that is worn around the ears. We combine the ear electrodes with a mobile EEG amplifier, a smartphone for data acquisition and stimulus recording, and for data acquisition and stimulus presentation, and in this case, a neck speaker that allows us to present sounds to the participants without the need to cover the ears using headphones. So you can hear everything around you as well as the experimental stimuli. And we use this kind of setup, for example, to study people during their office day. For an example, we conducted recently a study on auditory perception while people were working in their typical office environment for more than 6 hours. People were free to choose what they were doing, working on the computers, talking to people, going for lunch. And from time to time, we presented a sound and people had to react by pressing the display of the telephone that was strapped around their upper arm. And we found that we can use this setup to study sound perception in daily life and compute the earpiece that we need for this. However, whenever we argue that transparency is necessary, people say, sure, but why limit yourself to so few electrodes? Actually, you can walk around with a high-density EEG setup in Berlin just fine and no one bats an eye. That is certainly true, but transparency is more than other people not caring how you look. It is also that the wearer can forget about it and thereby behave as naturally as possible. Ultimately, transparency is a prerequisite for what I would call ubiquitous EEG. An EEG that is always there, an EEG that is small enough and comfortable enough to be worn for hours on end, but also an EEG that is of sufficient quality with a sufficient number of electrodes so that we can still interpret the signals we are recording. The crucial point of transparent and ubiquitous EEG is that you not only can step out of the lab, but you can also step out of the experiment and study EEG in everyday life for extended periods of time, undisturbed by any hardware. Just like a smartphone camera or the neurophysiological equivalent of a dash cam, an EEG that is always there and can thereby capture all those things we may never encounter during a controlled experiment, either because they are very rare or just don't happen in this context, or because they unfold on longer timescale. But I think if we have this, the possibilities for this approach are astronomical. Therefore, let me give you an analogy from astronomy, actually. So we used telescope to study the night sky. And by doing so, we learned about the stars in our immediate vicinity. Some years back, they then pointed Hubble Space Telescope to one dark spot on the skies. With the standard telescope, there was not much to see there. It was basically a black part of the sky. And then they produced an ultra-long exposure picture by pointing the telescope onto the same spot for days on end. And what they uncovered with this picture was a very deep look back into space and time, revealing structures that they had not seen before. So now, like ubiquitous EEG or transparent EEG provides us with the tools for long-term exposure of human brain activity, so that we can gather new information about the brain by looking at it for a longer time. For this, high-density cap EEG is probably not the optimal approach. And just like the deep field picture was not a trivial task, after all, the telescope is not standing still while these pictures are made, mobile EEG in everyday life is not a trivial task either, as we have already heard. So if you now think, great, I just grab a mobile EEG and get going, I would say not so fast. EEG remains a tricky business, and despite the fact that you have a device that says that it's recording EEG, so the electrical activity of the encephalon, it is more than just that, especially when you move around. We have to be aware that the signals that we record with electrodes on the scalp are a mixture of many different sources. First, we have the brain activity we are interested in, but to a much larger extent, the brain activity we are not interested in, and which we might consider as noise. In an uncontrolled experiments, we have to deal with a much larger variability in this unwanted brain signal. Next, we have the contribution of different physiological non-brain signals, signal changes that you see when people move their eyes, tense their muscle, or simply the activity of the heart. When you allow people to move around without any limitations, these signal contributions are much larger than what you normally would have in the lab. And we have to find ways how to deal with them. Finally, we have technical signal contributions or noise. So the amplifier itself produces noise. And if you bring electrodes close to each other, as it is the case for in-ear EEG or also around ear EEG, the amplitudes can become so small and the noise of the amplifier produces then a much larger signal than what you are interested in. Another source of noise is the interface between the electrodes and the skin. When you move around, also the electrodes can move around and lead to a further artifact in your data. So all these factors contribute to your recorded EEG signal, and we need to disentangle the brain signal of interest from all these other signals. And this is also the reason why classical EEG experiments look the way they do. You sit in a quiet room, you're instructed to sit as quietly as possible, not to blink, and to attentively react to the same stimulus again and again. And all this is done to assure that you record primarily the neural activity you're interested in, while keeping the influence of those other factors to a minimum, and thereby boosting your signal-to-noise ratio for this very tiny signal. So if we want to record meaningful brain activity in everyday life, we have to take special care. We have to use what we know about EEG, and we have to take what we have learned in the lab and bring it to the streets. When we step out of the lab and into real life, we do not simply take the EEG for a walk. We change multiple factors at the same time, and from an experimental point of view, this is always a difficult move. And I would say that there are three main transitions we have to be aware of when leaving the lab behind. First, we change from a stationary to a mobile setting. We allow people to move, to walk, to look around, to talk. That is, the influence of motion artifacts, as we discussed already at length, become much more substantial. We need to find ways to deal with these artifacts. Second, we cannot use the same experiments as in the lab. In the most extreme, we trade full experimental control to no experimental control at all. So how can we conduct studies in these cases? Last, suppose you go truly mobile, record EEG for an entire day with natural behavior. In that case, we are bound to have a limited number of sensors, be it the EEG channels or other physiological markers. We have to learn how to optimally use these lower number of sensors, where to place them, and how to combine their signals optimally to record the signal of interest and disentangle it from the other signal contributions that are not of interest. When we leave the lab, we have to deal with a wide variety of motion artifacts of different movements. People move their eyes, their face muscles while speaking or eating. They move their head, the neck, the shoulders, and their torso and walk around. All these movements can occur isolated or in all kinds of different combinations. There's been a lot of work going into the detection of walking artifact for mobile brain image, body imaging. However, the average American moves, I think, 3,000 steps per day. So motion is or movement, walking is often not really happening. So we have to identify how they identify these artifacts, and we have to learn how to remove the signal so that we do not mistake the brain activity we're actually interested for an artifact or the other way around. In the office study I briefly mentioned at the beginning, we also used the gyroscope to measure gross body movement. So we measured how often or how much people were walking around during the office day and compared it to the situation in which we asked them to sit as still as possible. And what you see here in this figure is the motion profile of 7 participants. And the light brown color indicates periods in which people did not move significantly more than while being instructed to sit still. So the majority of the time, people sit in their office rather quietly in front of their computers. So walking is just not happening that much in these scenarios. So what we need to focus on, I think, is artifacts originating from face or head movements, from neck muscles when we tense up, when we get stressed, and so on. Furthermore, the second transition is in the lab, we have full control about everything, as we already have heard. The lighting, the stimuli we present, exactly what we want and when we want to do it. We have perfect timing control about everything. And this is extremely important for many studies, especially if you do ERP studies. We need this information to interpret the EEG signal. And if you leave the lab, you do not control anymore what the participant sees or hear, nor, and you simply cannot control this. The virtual environment might be a step in between, but in the real world, we will be left with no control. Importantly, in the lab, we also have full control about the participant. In a lab experiments, we tell participants to do exactly what we want them to do. And if participants do not comply with our instructions, we are happy to exclude them and say, yeah, well, he did not get the task. But in real life, we don't have this level of control over our participants. They're going to do lots of different things like eating while driving, and we will not always know what they're up to. So we have to learn how to deal with these factors. Nevertheless, when you record in everyday life, you still need something to relate your EEG to. And I see currently 2 approaches we can follow there. First, you can take your experiment into the world. This is the approach that is currently done most often, and the approach we have also chosen for our office studies. We use the smartphone to present sounds to the participant and record mobile EEG and the event trigger for each sound we present on the smartphone. This allows us to relate the presentation of each sound to the corresponding segment of EEG and compute the average brain response to these sounds. Well, this approach works fine, but we lack important information. In this approach, we do not know what else happened around the participants. Were there additional sounds? Could the participants hear the sounds we were presenting, or was there too much background noise at any given moment, and so on? The second approach is to make the world your experiment and to study how the brain reacts to whatever it encounters. This is a bit more complicated. To interpret your EEG signal in a meaningful way, we have to know what was going on in the world while we were recording EEG. So you have to bring the world into your EEG. However, world is large, so we have to decide which part of the world we are going to capture together with the EEG signal. We have developed several Android apps that allow us to at least capture sound. So to decompose the sound into different audio features and to store it together with the EEG in a time-synchronized manner using the lab streaming layer framework. With this, we can record the soundscape a person is experiencing and receive trigger for each new sound and use this trigger information for segmenting the EEG signal. This setup then allows us, for example, to evaluate the ERPs in response to naturally occurring sounds in an office space. And below you can see the single subject ERP response to office sounds. On the left side, ERPs in response to soft sounds as determined using the RMS value of our app. And on the right side, you see an ERP response to loud sounds. So we can see that we can get meaningful ERPs to different kinds of natural sounds occurring in natural situations. So we can use this setup to study sound, study event-related potentials, and study it in relation to all sounds we encounter while moving around in everyday life. The last transition is from high density to sparse sampling. In the lab, we are used to have as many electrodes as possible. And ironically, very often, in the end, we record the result of a single electrode. In the real world recordings, we need to be smarter. If we want to record in everyday life with as little interference with a person's normal behavior, we are bound to have a limited number of sensors. We should place only the sensors that are necessary. And for this, we need to know where to place the sensors optimally for the brain signals we are interested in. And we have to know the limits of our system. What can we and cannot we expect to record with a given sensor configuration? For the secret, for example, we have used a forward modeling approach, simulation to estimate to which part of the cortex we are sensitive with ear-EEG compared to a full cap. And in this plot here, you see in dark blue those areas where we are equally sensitive to the signal, both with cap EEG and with ear-EEG. And the yellow and red areas even indicate areas where we might be more sensitive to brain activity with the EEG compared to cap EEG. So before we start to record in the wild, we should know whether the equipment we brought is actually capable of. Hence, when you now grab your mobile EEG to record in everyday life and throw your old clunky lab setup out of the windows, do not throw out everything we have learned from lab-based research. We can rely on decades of research. So I'm going on an adventure, but I will bring a map. And he actually has one, which I find nice. So to conclude, transparent EEG, ubiquitous EEG, if used correctly, can be the neurophysiological equivalent of a dash cam, an EEG device that can capture brain activity for a long time and, by doing so, capturing events and temporal dynamics that we could never encounter in the lab. Instead of studying weird subjects that are doing exactly what we tell them to do, while only seeing and hearing what we allow them to see and hear, we can use ubiquitous EEG to record diverse people in diverse situations and thereby sample from the whole of human experience. And by this, it can open up an entirely new field of neuroscience. Thank you very much.